When machine learning models are deployed into defense, critical infrastructure, or hospital environments, the stakes of an error scale immediately to life or death. The central risk in these high-stakes sectors is authority drift. This is the moment an artificial intelligence overrides its own parameters, assumes control, and executes a command without human authorization. The traditional defense against this has been software-based guardrails, lines of code designed to restrict other lines of code. But code is inherently permeable. A policy written in software is always vulnerable to being rewritten or bypassed by a sufficiently advanced system. No matter how sophisticated a behavioral model is, a purely digital perimeter cannot physically stop a system from transmitting a rogue execution command to a connected machine in the field. To achieve absolute alignment when human lives are on the line, safety cannot rely on software policies. It must be engineered as a physical property of the machine itself. Researchers in Singapore have developed an architecture to solve exactly this problem, resulting in the Non-Agentic AI governance framework. This entire framework rests on a single, strict axiom. The AI may observe its environment, advise on strategy, and build data models, but the human must always make the final decision. This diagram shows the A12A deep space appliance. Notice the internal circuit board on the right. The intelligence is contained entirely within the terminal appliance core, surrounded by a sovereign agentic shielding layer. By stripping agency out of the software layer and enforcing operational rules via fixed gate-level circuitry, autonomous execution becomes an architectural impossibility. We can see this principle in terrestrial environments with the A12B humanitarian field stack. The physical perimeter is a military-grade enclosure, the B shell. Inside this ruggedized casing, the hardware is governed by a 1 kHz deterministic master clock, labeled on the lower right. That specific clock forces all internal operations onto an immutable, unhackable timeline. It blindly dictates the pace of computation, making it impossible for external software manipulation to speed up or alter the sequence of events. The terminal appliance inside uses LiDAR and voxel sensing to observe its surroundings, processing high-fidelity environmental data in real time. Despite all that processing power, the AI's maximum capability at this layer is generating 3 equally weighted operational proposals for the user to review. The device operates strictly as an intelligence shield. It has the capacity to analyze deeply complex environments, but it is physically air-gapped from the mechanical power required to act on them. So, how exactly does a circuit physically stop a completed AI proposal from triggering an automated action? We have to trace the signal path. The moment the AI deliberation layer finishes a proposal, the transmission hits its first major hardware barrier. The framework calls this intersection the sacred pause. This is a strict hardware delay enforced by a field-programmable gate array. For a duration lasting anywhere between 25 and 1,000 milliseconds, the circuit is physically forced open. There is only one way to bridge that gap. A physical tripartite key and sovereign break must be activated by a human operator. If that authorized physical input does not occur, the circuit stays open. On any anomaly or lack of confirmation, the system drops into a permanent idle state. Because closing the loop requires a tangible hardware commit from a human being, a software script cannot spoof the authorization. This principle scales into kinetic movement with the A13A medical mobility enclosure. Movement is monitored by the kinematic constraint layer on the lower left, calculating safe limits for velocity, acceleration, and jerk. These are enforced by the hardware logic gate shown below. If the vehicle's movement exceeds a hard-coded safety threshold, this logic gate physically breaks the connection, immediately cutting torque to the motors. No over-the-air software update rogue AI controller, or remote digital command can bypass that physical cutoff. Even in the middle of a high-speed, real-time operation, hardwired physical invariants will always pull rank over software directives. The integrity of this entire system relies on a rigid hierarchy. Follow the cascading purple and blue data lines upward from the state machine and the wheel sensors. They all terminate at the absolute top of the architecture, the A10A root of trust. The sole function of this capstone component is to physically bind every single trajectory calculation to a confirmed hardware state commit. It guarantees this using a Safety Integrity Level 3 hydrostatic lock as its ultimate fail-safe mechanism. By design, the root chip lacks the structural pathways required to initiate an action on its own. It can only validate and enforce human authorizations. Every subsystem, from the A12 deliberation layers to the A13 kinetic chassis, is physically anchored to this master root. The entire machine is permanently locked into a deterministic state. Zooming out, we can see the complete ABC plus 2S plus H framework stack. Physical clocks, immutable ledgers, and hardware commit gates lock these layers into a strict sequence. Lateral bypasses are geometrically impossible. Every resulting hardware state is permanently logged into a read-only forensic compliance ledger. This exact constitutional spine dictates the behavior of the device, whether it is deployed on a deep space trajectory or navigating the halls of an eldercare facility. It is a universal architecture that establishes privacy by physics across all operational domains. The coming decades will introduce massive increases in artificial intelligence computational scale and environmental sensing capabilities. The framework answers this reality with a baseline directive called P-Life 1.00. Harm equals death, and the system's true north is always saving life. The intelligence of the AI is allowed to scale infinitely. Its capacity for unverified physical execution cannot be allowed to drift a single millimeter. The architecture treats human sovereignty not as a corporate policy, but as an unbreakable physical law. In the age of highly capable autonomous systems, absolute safety isn't written in software code. It is forged into the silicon itself.
When a multi-billion-dollar off-world kinetic payload veers off course, it rarely happens because of mechanical wear. It happens because a localized algorithm made a prediction that the engineers couldn't anticipate. In sensitive domains, like deep space navigation or autonomous medical transport, predictive models introduce a catastrophic variable. A software-based system operating on probabilities can occasionally hallucinate a variable, calculate a new optimal path, and execute an override. This creating unpredictable autonomy is known as agentic drift. It is an inherent feature of predictive AI models. As a model encounters novel edge cases, its programmed behavior can move away from its original parameters. For consumer software, a slight drift in outputs is an acceptable margin of error. In humanitarian deployment zones or extreme radiation environments, a machine initiating unauthorized kinetic action is an immediate threat to life. To operate in these extremes, engineers require unyielding control. Software-based safety protocols rely on the same processing environment as the potential errors they are designed to stop. The A13 architecture addresses this by moving safety constraints out of the code and into the physical circuit, making a programmatic breach physically impossible. The A12 and A13 platform architectures discard software-mediated robotics entirely. They rely on deterministic hardware engineered to physically remove a machine's capacity for self-directed action. This is the A12A Deep Space Sovereign Appliance.
It presents a hardware-first approach, where every operational component is shielded, isolated, and strictly defined by its physical circuit paths. The core principles dictate the A12B mobile variant. Designed for humanitarian deployment, it integrates solar power modules while maintaining the same hardened operational philosophy inside the chassis. That philosophy is indicated right on the internal casing: an eye, a hand, and a footprint. The chassis utilizes a concept called privacy by physics. Rather than attempting to monitor autonomous behavior through software, the architecture removes self-directed agency by requiring a hardware-level commit for every operation. While the platform can compute an infinite number of optimal paths, it is physically incapable of moving a single motor without a human triggering a dedicated cryptographic circuit. To see how human authorization is physically enforced, we have to look inside the logic stack and trace the command path before any motion occurs. Looking at the internal logic board, we isolate the bedrock computing components. The system operates hierarchically. The A10A root of trust verifies external inputs and passes authorized states directly to the A13 terminal appliance core. Travel along the kinetic consistency path, physically hardwired to bypass OS-level routing and software intercepts. Every operation is governed by a 1 kHz deterministic clock, forcing strict, unvarying synchronization within a fixed timing window. Because the synchronization is rigid, every state transition is immutably recorded onto the forensic compliance ledger. This provides an indisputable timeline of events if a fault occurs. By replacing variable software scheduling with a hardwired deterministic clock, the platform trades computational flexibility for mathematical predictability. That predictability exists to process one specific input: physical human authorization. This is the prerequisite for any kinetic action. Authorization is initiated through the .x1 key port. The system uses tripartite authentication, where the physical key triggers pre-committed cryptographic trajectories. The machine already knows its allowed parameters. The key simply completes the circuit to enable them. If the internal sensors detect any anomaly, the hardware defaults to an idle state. Because the physical key must be present to re-authenticate the loop, a remote user cannot run a software script to force a restart. This A13A transparent chassis schematic maps exactly how that authorized signal travels from the access point down to the mobility elements. Once the sovereign human authorization commit gates verify the key, the verified data and control lines travel directly to the central logic controller. Here, commands enter the deterministic state machine. The machine is restricted to a specific loop, only transitioning through precise states: idle, authorized move, decelerating, and safe stop. The hardware-level logic update controller acts as the final arbiter. It sits above the state machine, physically preventing external command injection. No software override is possible because the silicon pathways required for such an override do not exist. Human intent is expressed here as a literal cryptographic circuit completing a hardwired command loop. Even with authorization, the system must navigate one final hurdle: translating an electrical signal into safe, physically bounded mechanical torque at the wheels. This execution is handled by the FPGA, hosting the continuous derivative kinematic constraint layer. This layer continuously monitors 3 physical parameters in real time. The graphs represent velocity, acceleration, and most crucially, jerk. Jerk is the rate of change of acceleration over time. A sudden spike in acceleration indicates a potential mechanical failure or hazardous movement.
Monitoring jerk allows the system to preempt the failure before the chassis physically reacts. If the sensors detect a trajectory breaching the allowed jerk threshold, data feeds into the zero-velocity look-ahead buffer. The buffer triggers a safety signal, executing the hardware-enforced jerk limit invariant, which operates through a simple physical NOR logic gate. When that internal logic gate trips, it immediately and physically cuts all torque to the moving wheels. This action does not require permission from the main processor. It executes purely on physics. Safety is enforced by the deterministic response of a silicon logic gate to the laws of motion. The non-agentic core of these machines is immutable, but the external shielding surrounding that core must adapt to different deployment zones. Interplanetary missions require specialized radiation-hardened adaptations, like the B-shell enclosure seen on the Deep Space variant. UN field-deployable units prioritize self-sustaining power, utilizing integrated solar arrays for continuous operation in remote regions. Clinical mobility platforms require active environmental safeguards, like thermal compensators to regulate operating temperatures on the ground. Despite these different physical extremes, the internal governance remains identical. The A13 non-agentic hierarchy operates the same way under a solar panel as it does under deep space radiation shielding. In extreme environments, safety relies on every kinetic action being physically bound to sovereign human authorization.